Welcome to the video lecture. Today I am going to explain about uh, magnetic force of a single excited system from Coenergy. In this session I am going to derive the force equation from Coenergy. You know the already two state functions, one is the field energy, another one is the coenergy. The field energy in the differential form, it is called WFLE, is a function of lambda comma x is equal to id lambda minus force into dx. Similarly, in the last class we derived the coenergy. It is also a state function, but the variables are state variables are I comma x. Here the value is lambda di plus field force to dx. So today, last class I derived the force equation from energy. Now I derive the force equation from coenergy. You know that any state function with two state variables like this, it is differentiated with partially differentiated with the two variables. First of all, individually dou x1 into dx1 plus dou f by dou x2 into dx2. But in first case, suppose you are differentiate with the first variable, second variable treated as the constant. Here in this differentiation, the first variable treated as the constant. This is the formula. Like this, maybe it is equation 1, it is the field energy, this is the coenergy, this is the mathematical phenomenon. Like equation 2, this is also coenergy, also it is a state variable with the two state functions I comma x. So we have to analyze this with equation 3. I can rewrite this coenergy is equal to I comma x is equal to dou of this coenergies differentiate the first state variable di dou into di plus differentiate dou x into dx. Here, yes, second variable treated as a constant, x is constant. Here the first variable, that is called I, is treated as the constant. This is equation 4. Just you have to observe equation 2 and equation 4. Similarly, here the coenergy, the value some lambda into some value into di plus some value into dx. Similarly here, here this portion is some value. You observe this. Similarly, this is the some value. You compare this equation 4 and 2. We observe what is the lambda value. What is the lambda value? Here the lambda is equal to, compare this one and this one, dou coenergy by dou I, but here x is called constant. Similarly, force equation, field force is equal to, this is the value, differentiation of coenergy by dou x, but I is treated as a constant. So you know the field energy, this is coenergy. We derived the coenergy, WFFLD dash is equal to, that is equal to half the function of LFX I square. We derived the same pattern we are applied for the energy. We are getting this equation. Simply this value substitute, maybe this is the value. We are getting, this is the equation 5, this is the equation 6, this is the equation 7. 7 is put into the 6. What you are getting? Magnetic force is equal to dou W dash, that is called as a coenergy with dou x. The I is treated as a constant. Just we substitute this dou by dou x of Coenergy is nothing but of L of x I square. Here I is equal to constant, that's why of I square directly taken outside, of I square dou by dou x of L of x. This is called, simply we are called as joules, newtons. So in the field energy force equation, in the previously we are calculating from energy, we are getting, this is the same equation of dou L of x by dou L of x by dx. Here also from Coenergy also, this is the equation you are getting of I square as dou L of x by dx. Simply it is the differentiation dx. Either it is the Coenergy or energy, the answer is similar. But in the single excited system directly, but here I observed directly this value is calculated from the current, but previously the field energy force, magnetic force, is calculated lambda square by 2L of x. Based on that we can calculate it. So this is the derivation of magnetic force for a single excited system from Coenergy. Thank you.